Thank you. 2 questions about recording was one. Yes, I just turned that on. And would we be able to do an alpha cleavage for the first one? Yes, there are fragmentation patterns for the first one that we would see. So you could, let's draw this again. Where's my drawing? Let's see here. See, if you break, do it like, if you break there or there, it doesn't really tell you anything because you're losing the same amount of stuff. You would need to break, let's erase this. You would need to break here to get that, to see a difference between the two of them. And in the second one here with the, if you're to lose the longest chain, if you do the same sort of thing with alpha cleavage here, like if you, the methyl group loss is this, you got 2 methyl groups here and you got 1 methyl group here. So for this alcohol, you would see the mass minus 15 peak, which you would expect it to be a lot larger than this one over here. But the alpha cleavage on the other side, where this goes there and that goes there, this goes there, you're losing a propyl radical versus an ethyl radical. So that would be a main one to, that would be a larger, like you wouldn't see a mass minus 43 here, I guess. 43 if my math is correct. I got a question for everybody. Which of these two would you suspect would have a stronger molecular ion? Yes, that's right. We would expect, like tertiary alcohols these would tend to fragment even faster than secondary alcohols. So I would expect that this one would have a stronger molecular ion than the other one. So those are basically some of the ways I would tackle this. You can, like with the second one, there's a McLafferty, because you got a long chain over here. You could do a McLafferty for this isomer and not necessarily for this isomer. So it's just digging up some fragmentation possibilities, which would be different between the two of them. There's a whole, like you, basically, when I asked this question before, I was just looking for one example that would seem to be useful. So for these ones where you could do the inductive cleavage, where you just move the, you would expect that you would lose a fragment like this or a fragment with the methyl group as well. So those are some possibilities as well. Let's see, let me erase this. So the math is 155, and we are looking for the various base peaks here. Did anyone do these ones yet? Okay, so let's look and see what we can do here. Okay, so let's think here. Where is my little draw? Okay, drawing. Okay, so whenever you have a heteroatom, let's redraw this. Remember, the electron which tends to be knocked off first will be the lone pair electron because it will be the highest in energy. Okay, so if we knock off this nitrogen's lone pair, then we've got a little electron here. So I guess the first thing I would do is I would try alpha cleavage on this just to see if it works. And so if you breaking the ring isn't going to actually change the molecular weight if we break this bond or this bond, because it's going to be this, nothing's actually unattached. But if you break this, it's entirely possible that we would get something. So if this goes there, that goes there, and this goes here, what this gives us is this plus, and then we have 1, 2, 3, 4, 1, 2, 3, 4, and then a radical. And so 4 carbons equals 48, and then the protons 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 protons equals 9. So this equals 57. And if our original molecular ion was 155, 57 minus 155 is 98. So this looks like that could be the base peak from that cleavage there. Now 165. And we are basically losing 45. So what could this be? I think I know. Okay, right. Okay, so this one is a bit, this one's a bit more number of different possibilities here. Okay, so let's pretend that we are going to lose a electron here. So we've got 3 different 3 different heteroatoms. In fact, so we won't, like this, the nitrogen lone pairs are actually delocalized in here, so they would probably be harder to remove. We need to lose 45, and so this nitrogen in the ox, that's 16, so we're not going to worry about those 2. So it's going to be over here, one of these 2 oxygens, which has got the whose electron is going to be. And I don't think it really matters which one we choose, because we can mechanistically figure it out from here. So it's the ester group which has got a fragment. If we try to fragment here, for example, just because we want to try that, the total number of atoms is going to be, it's going to equal more than 45, right? Because 1, 2, 3 carbons is 36. And then we've got 2 oxygens plus all the hydrogens. The oxygens are going to be 32. So that's way higher. Although I bet that this loss of that group is probably something in the spectra. It turns out that the fragmentation ion is right here. So we could do it one of 2 ways. We could lose the say, one of those lone pairs and just do a straight up sort of inductive version. So you generate this. Okay, so we've got carbons, which, so 2 carbons is 24, 5 hydrogens is 5, and an oxygen is 16. So this is 45. So that's correct. And so this would be the little undetected radical species, and then the other fragment would have the positive charge. But if we, even if we did it this way, where we lost that, so this is the positive charge here. If we move this electron here and this electron there and that electron there, you're still going to generate the same 2 fragment pieces. Okay, Kat, I'm trying to teach. So you get to go outside, yeah. Mass spec is actually quite tricky to analyze. So typically the fragmentation patterns, if they were ever to be asked, would be really hopefully straightforward things like alpha cleavage over here, and this inductive sort of breaking over here. But does that answer your question? Was that sort of what we had going? Okay, good. Let me erase all this mess. I was using the PDF drawing function and not the Zoom one. The Zoom one, you can clear everything at once. This is kind of a pain. Were there any other questions about the things on the midterm? Right. Can I explain MALDI, Fab, and SIMS again? Sure. They're all very similar, actually. The only difference is what they're using to bombard the matrix. Okay, let's see here. Maybe I can go into share a new screen, the whiteboard. Okay, so. Okay. So. So all 3 of these, MALDI, Fab, SIMS, these are all I think absorption methods. So, oh, they erase that. Erase that. I can't do that. All right. Okay, so you basically have your sample, and these are used for samples that tend to be non-volatile. So these can be larger molecules. So remember, for mass spec, we want to be able to take your sample and get it into the gas phase somehow. And so with smaller samples, like some things you can just putting them in the vacuum by itself is enough to, they're volatile enough that'll suffice. But the key point is that you got to get everything in the gas phase, and then you can ionize it, and sometimes this process is the same. And then once it's ionized, it's going to fragment, and you got to detect it. So with larger molecules, there's one of the methods that they used was that you'd put your sample into some sort of matrix. And so the matrix was, and let's say our sample is this colored thing here. So it's in this matrix, and the system up here is basically under, it's going to be under vacuum. And so the matrix tends to be something which isn't particularly volatile. Glycol is one of the thiol glycols as well, is one of the typical matrices. And you basically kit this with, depending upon the technique, something which is going to eject everything, and then strip it finally, and give it a charge. So typically, another thing is sometimes these matrices actually have cations in it, like potassium or sodium and that sort of stuff. So sometimes your molecule, when it's got that charge, it's a mass plus, say, sodium plus, or mass plus potassium. So the potassium is actually the thing which is glommed onto your molecule somehow, and that's in part of the charge, or it could be a proton, whatever it is. Now, depending upon what are you hitting this thing with, which is going to cause it to be ejected, and then the vacuum and the kinetic energy of the whole system starts to shed out all of the other matrix molecules, so you're stuck with your charged species. And it's basically the technique which is what's doing this. So with MALDI, it's a laser pulse. So you're hitting it with a laser. And as laser technology has gotten better, particularly the length of time that the laser's used, this has become more and more popular sort of technique. Fab is, you're hitting it with a stream of, what is it, xenon molecules with a huge amount of kinetic energy. So Fab basically is the fast atom bombardment. So you're hitting it with the xenon molecules that are with a huge amount of kinetic energy. And SIMS is, you're hitting it with cesium, a charged cesium atoms, ions, I guess I should say, that are doing the same sort of work. So this is basically used for non-volatile large molecules, and it's put in a matrix. The matrix is slammed with various sort of either the laser or the xenon or the cesium, and the kinetic energy or the heat from the laser pulse, it's going to blow these things apart, and then gradually you shed the matrix molecules and you're left with a charged species. So sometimes it is like a mass plus proton. That's basically how those work. I think in our notes, I did talk about the various types of matrices for the various things. No, I don't think it's particularly important. Like with that gives me that's right. Like with MALDI, sometimes they use photosensitizing molecules, which helps in the process. But no, I think those are added details that we're not really interested in. One of the key points here is that you wouldn't need to use like MALDI or FAB or SIMS on like a small, tiny molecule. It would be far simpler just to use like chemical ionization or electron impact ionization to do that. You need these for larger biomolecules and that sort of thing. And it's similar to with electrospray. So you got your capillary, and it's shooting out your sample surrounded by water. But this is charged, so it's imparting a charge on the whole system. And then the charges, if this is a big globby molecule and there's like a flow of nitrogen in the opposite direction, Coulombic sort of repulsions break these down to smaller little globules. And then this countercurrent of nitrogen, or a neutral gas, would be nitrogen, makes it lose the water, and you're basically stuck with a little charged structure. And sometimes it's your mass just with the plus, and sometimes it's mass with a hydrogen attached. And of course, there's a negatively charged electrode over here, which is helping deliver your sample in this direction, although nitrogen's going the opposite way. But that's a nice technique which you could use for basically anything. But because you can with electrospray ionization, you can have an HPLC attached to it. The big advantage to this is that you can, if your sample you're analyzing is a mixture of compounds, the HPLC can separate those out, and then you can get the mass spec of each component as time goes on. So that's nice. So the advent of being able to attach an HPLC to this sort of mass spec was really, really useful. So I don't know if everyone's taken, when do you guys do HPLC? Do you do that intro analytical, or do you do that in instrumental methods? Yeah, so there's a little bit of yeah. So if you haven't taken intro analytical yet, it's just a chromatography technique which happens to be done under pressure. So, but yeah, it's a way of separating out. If you've got a mixture of stuff, you can separate it out into A, B, and C, and then A will go through this, and then B will go through it, and C will go through it. And it's a really, really useful. Electrospray is really, really useful with regard to that. Okay, now what else do we want to talk about?
I was just wondering, how many spectra will we have on the test?
2. And each will have, it's going to be a proton and it's got an infrared to help. So, and no, there's no C13 on the midterm. So with the 2 of them, hopefully it will become, because remember with infrared by itself, sometimes the structure, there'd be a couple of potential possibilities, but with the proton attached to it, we'll be able to get it down to really just one possible structure, I think. So you'll want your proton correlation table and your C13 correlation table. I'll actually post those on Moodle as well, so it'll all work. So we'll do the exam basically like we did it last time. You can download the test through Moodle and upload it through Moodle, but we'll use the Top Hat Proctorio thing to just basically monitor the test when it's going on.
I was just wondering if you'd be able to set up another like sample testing on Top Hat so I can see if like my mom's computer will work with the Proctorio since it didn't work on my computer last time.
Okay, yeah, I can do that. What I'll do is I'll just reset the old one and just reopen it.
Okay, thank you.
Yeah, I can do that. Okay, so let's just clear this for a second then. There is a question about the quadrupole mass spec. So in there was and so we call this I guess we should call it a magnetic field. Magnetic field, electric field, all part of the same sort of thing. So remember in our magnetic sector, mass spec, you had your ions and they would travel and then they would be deflected because of the electromagnet and they would reach the detector and you would scan from low to high and only like the lower mass ones or the higher mass ones, or actually I guess the lower mass ones would be deflected more and the higher mass ones would be deflected less. But in these types of spectrometers, it was you've generated your ions and they're being deflected by the magnetic field, and only certain ones would reach the detector. And so these are basically the first generation mass spectrometers. And they took up a lot of space. If you go to like some of the larger universities will still have these mass specs, or some of the really instrumental labs which are doing like contracts for whoever it might be. You'll still find these mass specs and they're quite big. I remember when I was at Waterloo, there was quite a large one at their facility. The quadrupole is it's basically a very similar sort of philosophy associated with it, but instead of having a large electromagnet, it's got four electrodes, which are basically all lined up as it's just with a series of and your ions are going to travel down in between all four of them to come out the other side. And depending upon the and I guess they take a quasi spiral path when they go through it. And if they're not tuned just right, and I think they use the word resonant. If they don't resonate exactly right, they're never going to make it through to the detector. And they'll zoom off, they'll be deflected off. So there's only one mass will make it through at any time. So you'd scan from low to high, and you would reach the detector. So the difference is that, but these things are tiny, like they're like the size of a pen or even smaller. So it's a tiny little system. So the mass spec itself it'll fit on top of a bench top. So if you go into Dr. Chen's lab, he's got one of these leaning against the wall in his, not in the mass spec lab, but in the research lab, right behind his big, what's the thing? His microscope. On the wall behind his microscope, there's one of these, and it's a tiny little, it's not a very large box. So the quadrupole works, the philosophy is similar, except for the only thing is that the ions are traveling in between these, I'm saying electrodes, but I don't know if that's actually technically the right word for it. And they've got a charge across the top of them. So only certain ions will make it through depending upon their mass. And all the other ones will be deflected. But you're still basically doing a scan from low to high and detecting each ion as it reaches the detector as you go along. So, but the main difference is that these things are these are small or tiny, and the large magnetic sector ones are big and bulky. So they work similarly, but slightly differently. Their size is different, their cost is different. And this is, yeah, and there's quite a few things you can actually do with these. It's too bad that we're in this COVID era, because Dr. Chen gave basically a tour of his things last go around, and we would do some he'd explain some more sophisticated mass spec techniques. But if you're gonna take so that's basically the quadrupole. Yes, I meant the IR and NMR correlation tables. Yeah. So we'll need the IR correlation table and the proton NMR correlation table. Did that answer your question about quadrupole? Okay. Was there anything else? Yeah, so it'll be 2 hours for the, I don't think the theory questions are particularly difficult. I don't think so. I think some of the questions, if you can do the questions on this, some of the questions on this are slightly more challenging than anything that I've got on ours, I think. So if these all If you can answer all of these, then I think that you will do just fine. Yeah, and basically these are all the theory questions I had on previous tests. And each year is slightly different, so you cover things in slightly more detail. And that's, excuse me. One year we did a lot of work on fragmentation stuff, so that's why these sort of questions were in there. How was everybody's break?
Pretty good. Didn't really do much. What about yours?
Yeah, it was it seems like class, it seems like it was a very long time, in all honesty. Maybe it's because of all of the stuff, code red stuff, which was going on, but it seems like between this class and the last class that we had, it just seems like it's almost, it seems like it's been like months, which it can be a good thing, or or it can be a bad thing. Yeah, I meant to do more fun things too. Yes, the theory is just going to be on mass spec. Okay, well, if there's no other questions, I'll set up another practice test thingy, just to see if the Proctorio works. And besides that, there is the Proton assignment, which was sent out, which isn't due until a little while. But if you can do, like, those would be really good practice questions for the midterm. I think the ones that I've got will be less challenging because we've got a limited amount of time, but we'll see, I suppose. Okay, so I'll post this actual lecture on Top Hat as well later on today. All right, if that's it, then I will see everybody on Thursday. If you have any questions, just email me. I won't be running around anywhere anymore, so if you have any questions, just send me an email.
Thank you.
All right, see you.
See ya.